you hear me now? I'm sorry.
Yes.
So thank you again for the introduction. My name is Alexander Oppermann, and I'm a researcher at the National Metrology Institute in Germany called PTB, or Physikalisch-Technische Bundesanstalt. I'm presenting today a research project called Angewandt, which has a 3-year lifetime, and there's a joint project with industry partners called Paus, Kienhofer, and Freund. And their focus was a new business model with hybrid added values for scales and construction vehicles. And I'm focusing in this talk now on the development of methods for supporting metrological processes in the public domain and the prototypical implementation. So our project aims and challenges were that we needed to rethink and reinvent sovereign processes, and we had to analyze thus the existing processes and deduct the requirements. In the end, it came down to what part of the processes and their chain can actually be digitally transformed, and we have to dismantle reservation against technological innovations of our partners. So we had to build up and reinforce trust in the digital enhanced processes and digitally domain, and ensure, of course, the same level of security in digital transformed processes. So we came up in the 3 years with a platform that I'm sorry. So were started with the digital verification application and the digital software application. And these are 2 applications that are carried out by the owner of the manufacturer of the measuring instrument in the field. And these are obliged by law. Then we built actually a service around that. That's called the digital device path, where we can retrieve measuring instrument data from the field from this measuring instrument, and can save this in a digital common data service where we can reuse this data. And every application we are able to archive this in a digital archive service. Today we will focus on the digital calibration application service and the exchange format called the DCC, the Digital Calibration Certificate. Also, we shortly dive into the digital Declaration of Conformity. So we deduced some requirements for these 3 services. Basically, it was we needed an easy way to up and download these conformities and certificates and passes. It should be easily available, accessible. It should be always have recent data from the field. The data should be reusable. While you upload the data, it should be validated. It should be signed data. It should be access protected, so not everybody can access this, and only people who have the roles to access should access it. It should have a machine-readable exchange format and also a human-readable format available. It should be archivable. And what you see here, the certificate is always a result of the process. So diving now into the applications, we have several more requirements. So we wanted to connect external infrastructures because they are not always in the domain for the National Metrology Institute, but also in the domain of partners, like the market surveillance, for instance. We wanted unified interfaces. So we deduct REST interfaces for our platform. It should be always a formalized workflow. We wanted the avoidance of switching tools. So we wanted to avoid basically that if you're in certain parts of the process chain, you shouldn't take the phone and ask to advance the process, but always use the same tools. The procedures should be streamlined by the digital transformation. It should be a transparent process change, so you always know where you are in long-running processes and you're not in an obscure loop or something. We wanted to achieve an efficient use of existing resources. An intuitive workflow would be achievable. And of course, as we stated before, in validation of data, signing of data, all these requirements also acquire here. So now we just dive into the platform on detail. So we have basically here the Untitled platform, which is a loosely coupled service platform. So you have here for each service one module. You have here the identity and access management solution. And we have here cross-functional services, as we already told you, the document storage services, the archive service, and the common principles data service is when you already like apply for a recalibration that you can reuse the administrative data in several different services again. Then down here we have the external infrastructure that we connected to our platform. Here's the vacuum laboratory that we are gonna see right now. And then we have the calibration application service, which is from the markets and user surveillance for recalibration of measuring instrument. And then we have the manufacturer cloud, where we retrieve the device passes and the data. And now we're gonna shortly dive into the digital calibration application. And yeah, it's not that complicated. So basically we have here the application, the Angewandt front end, the Angewandt platform, and here's the external resource, in our case, the vacuum laboratory. And so our user wants to recalibrate its measuring instrument and starts to create a request. And this one fetches from the vacuum laboratory all the to-dos, all the measuring instrument they are capable of recalibrating it, and then retrieves then the answer in the front end. And we have here a drop-down menu, so there's no free text. So the first error prompt process is actually avoided, while you have avoided free text. Then we, in the end, when we are done and have our administration services data applied in our form, then we send the request, and now their workflow is actually started. And we receive a confirmation, and then when they are starting the measurement, we get a status update that they are now actually are in the measurement phase. And then once they are done with the measurement phase, then we get a status update with the analysis phases. And then in the end, once they are done with all that, then we get the status that there is a certificate issued and the process workflow is actually completed. So we are able now to request this certificate and persist it in our archive service, as you can see up here. So we are here now in the archive service, and our user down here can actually download it or can forward it to any body that actually requests such a certificate to see. And here you see now the workflow from our partner. And this is actually, we didn't change any workflow. What we did basically, I'm sorry to switch, is that we created an interface here with the REST interface. And we actually get here then via this REST interface, the status updates and the request service. So what we didn't have any influence on their actual workflow in the laboratory, and this was it's really necessary because we wanted to avoid a high change, a high pressure for them to change, and only wanted to connect to the infrastructure and get the most out of it. So we avoid these data silos that they are all around. And here you can see we get the list of to-dos, we get the status updates, and in the end, they basically create this DCC XML exchange format. And this is actually how it looks like. So this is a digital calibration certificate service. Here you see the XML readable, machine readable format, and here you have the official rendered HTML human readable format. So this is how the Angewandt platform actually looks like. So you have here a menu, and you can say that you wanted to have a calibration certificate. And then you see here the already applied certificates in a list. And if you want to see the details, you basically click down on here. And then you get all the details of what kind of status is my application, when it is going to be ready, when it is going to be applied, what kind of to-dos is for my measuring instrument done, and so on. And in the end, I can download the certificate basically and import it into my archive service. So now we dive into another service was called the Declaration of Conformity. This is actually when the manufacturer has to declare that this measuring instrument is applies and valid with the direction of the European Union. And we here cooperated with SmartCom, and they actually gave us just the XML schema. And we actually could provide our modules because we already did an upload service. So we know already how to validate this data by the XML schema. We did the converting from XML to HTML. We wrote the XSL template, so we have the style sheet already done, and we could archive it, and we have really no hassle because of the modular way we constructed our platform. We could easily connect it to our front-end service. And then we gave them basically just the module of the archive service and the DOC service, and I gave them the backend services so they could actually connect it with their front-end service. And this is how we cooperated with that. And this is basically how it looks like. It's very, very similar to the DCC service that we did beforehand. So we have here a Declaration of Conformity, an XML schema, and here we have the branded EU Declaration of Conformity, and here are the norms that they confirm that they are, that they did the tests and they conform are in conformity with. So basically, to sum up, is that we constructed a decentral and extensible platform. We connected external IT platforms. We formalized and transformed analog processes, and which is really, really important to us, were the future-proofed and harmonized interfaces. So we did everything, even the internal communication by REST interfaces. Always when we started to code something, it's always very important to us that we can reuse the source code and the concept we developed for our biggest sister project called the European Metrology Cloud, where we actually cooperate with all the European metrology institutes in Europe. And we were creating the foundation now for database services. So for digital twins, but also for machine readable and machine learning services in the future. And this two-factor authentication for our token user manager is actually something that we did, but we are working on open ID integration in the future, so we can use single sign-on services, which is actually very important because if we have external users, we can easily onboard them with their identity provider. So we don't have the hassle for the registration, for the same thing, for the application again and again. So you just take your company's identity provider and use their ID and onboard to our platform. Then we are now in the process to make our service hub available for our external partners. So it's not only internal, but now we're going public. And we are planning on implementation and administration self-service, or called Digital Twin, where we get all the administrative data and all the interesting data across the lifespan of a measuring instrument in one place. And of course, always having in mind that only these people get access to the data which are obliged to and allowed to. Then we want to migrate this infrastructure to a native Docker infrastructure and create Kubernetes cluster. This is basically the next steps we are working on right now. Okay, then thank you for listening, and I'm happy to answer your questions.
Thank you, Alexander. You're perfectly on time. So is there any question for Alexander from the audience? Okay, then I'll ask you just a curiosity. Can you go 2 slides back in the summary?
On the summary, I'm sorry.
Yes.
This one?
Yes. So you said that this is, of course, preliminary work or a basic work that will create the foundation for database services for the public sector. So I was wondering if you are already planning some kind of collaboration with the public sector, or if it's in the future, or maybe you already did it, I don't know. Because I'm interested in the, this digitalization of public sector.
Yeah, so I'm part of the public sector, basically. So the National Metrology Institute is
yes.
a national body, so a public body, basically. And we try to now to connect all these loose strings in Germany and to create a service, a new digital service infrastructure. So this is why we created these loosely coupled services, and we wanted to onboard external infrastructures. So we don't want to reinvent them or like say, okay, you have to use our platform, but show them actually that their efforts can be used and reused in smartly connecting their services and creating a service hub. So yes, we are working right now with the market surveillance, for instance, actively together to connect their services and efforts in the digital transformation of their procedures. Yes.
Thank you.
You're welcome.
Okay, thank you for the presentation. I think we are right on time. We can skip to the next one. So the next presentation will be given by Nikos Panopoulos. Did I say it correctly?
Yes, it's Panopoulos, but it's okay.
I'm
No
sorry,
problem.
I'm really bad at Greek surnames. So,
can I share my screen?
But I do like your accent, though. So the work that Nico is gonna present is about design and development of an edge computing platform towards 5G technology adoption for improving equipment predictive maintenance. That was a long title.
Okay, can you see my presentation?
Yes,
just
Nikos,
a moment.
You can start, please.
Just a moment. So, okay, now I think it's in a full screen mode.
Yes.
Okay. Hello, thank you for your kind introduction. My name is Nikos Panopoulos. I am a research engineer at the Laboratory for Manufacturing Systems and Automation at the University of Patras here in Greece. And I will present on behalf of my colleagues our research work entitled Design and Development of an Edge Computing Platform towards 5G technology adoption for improving equipment predictive maintenance. Now, let's move on to the next slide. Here we can see the outline of the presentation. Our presentation is structured in 9 sections. We will begin with the introduction to discuss the situation, to identify the key challenges and highlight the aim and the contribution of this research work. Then we will move on to the state-of-the-art trends and the main application scenarios for 5G technology. In section 3, we will present and discuss the proposed system architecture and the transformation rules between the UML model and the OPC UA protocol. Moving on, the system implementation section is described, and then we will analyze the data acquisition devices and develop the graphical user interface in the case study and development section. The presentation summarizes with some future work ideas, the acknowledgements, and the key references. Now, the recent technological advances in terms of information and communication technologies have led to the increased data sets, big data sets, and the computational devices have to face tremendous increases in demands in terms of computational power. A common trend during the Industry 4.0 paradigm is the integration of big data analytics, predictive maintenance technologies and techniques, and so on. Predictions have to be available to the equipment owners in order to schedule the maintenance plan and repair operations early enough without disturbing the current factory plan. It is stated based on our literature review that through the adoption of predictive maintenance frameworks, machine uptime can be increased up to 10 to 20%, and at the same time, the overall maintenance costs can be reduced by 5 to 10%. We have summarized the aim of this paper at the lower part of this slide. We can see that this paper focuses on the development of an edge computing platform to address the communication issues between the data acquisition devices and the computational frame. We have used the Open Platform Communications Unified Architecture Protocol, and the physical model that was represented as a digital twin was designed in terms of UML diagrams. Finally, we have developed a digital twin of cold chain industrial equipment to run some simulations and calculate the remaining useful life of the most important components of the physical counterpart. In this slide, we have used some interesting reports and statistics from literature, and we have seen that 5G and industrial Internet of Things are estimated to add close to almost $800 billion to manufacturing gross domestic product in this decade. And at the right part, we can see that the key technologies that will be boosted by 5G are the augmented reality towards remote expert, the precision monitoring and control, and the advanced predictive maintenance techniques. Additionally, this slide summarizes the technological capabilities of 5G and their implications to the users. We would like to focus on the low latency that is estimated under 10 milliseconds, the high bandwidth rates, and we will be able to stream Ultra HD videos on the go, the high capacity of devices per square kilometer, the high reliability of the networks, the mobility, data availability on fast-moving mobile assets like trains, cars, and so on. And one important aspect is the reduction of the battery life for low-power Internet of Things based devices. Now, in this slide, we have summarized the industrial application 5G spectrums. The industrial applications for 5G are dependent on access to appropriate radio spectrums. Based on the capacity and the wavelength of 5G, 3 bands, frequency bands can be identified. The first one is the low frequency band under 1 GHz. A characteristic example is the wide area logistics or sensor networks. The second is the mid frequency band in the core of 3.3 to 3.8 GHz. A characteristic example of this band is its use in public mobile network operations. And finally, the high frequency band, known as the millimeter wave. We can see here the details, more details on the spectrum range. And this is the band that is used towards wireless networking in flexible production lines, machine vision, and supply chain management. And here we can see the coverage and capacity, as well as the design of the cell network infrastructure in comparison with the 5G wavelength. Now, To summarize our introduction, the edge computing is a must-have capability for service providers because it facilitates new business models and can improve profitability. As a distributed form of computing, it is designed to reduce bandwidth, to improve response times, and edge computing also enables operators to deploy some services closer to enterprise customers. Some challenges identified are focusing the security, and in our case study, this is a critical factor for edge clouds in cold chain equipment. And our challenges can be addressed with the design and development of an edge computing platform in order to distribute the computational load to the nodes, and by extension to enable the utilization of machine learning techniques for the calculation of the remaining useful life of identified critical components. Moreover, the framework promotes the utilization of 5G cellular networks to take advantage of the low latency and increased bandwidth. Some state-of-the-art key publications in the field of predictive maintenance and digital twin have been summarized in this slide. Under the framework of Industry 4.0, there are several techniques and technologies presented in these topics. The main goal is to achieve the full digitalization of modern manufacturing systems. Modern manufacturing systems have transitioned to cloud manufacturing paradigm in order to transform the business models towards servitization. A huge amount of data derived from a variety of smart and connected devices is left unused, as we can see in Professor Murgi's publication. Moreover, due to the increased amount of data produced, there is constantly increasing need for more and more computational power. In order to enable the prediction of future malfunctions, higher level architecture for interfacing physical equipment with the digital twins is continuously implemented, and the utilization of support vector machines as a suitable technique for data processing is identified in literature. Like here we can see a very important slide which summarizes the 3 typical application scenarios of 5G based on the International Telecommunications Union. I would like to move on now. We can see the reference architecture for edge computing. We can see the 3 layers, the software layers with the data acquisition devices and sensors, the edge layer, and the cloud layer. At the left part, we can see some market drivers. Now, as it regards our proposed system architecture, is based on the utilization of a microcontroller unit for the integration of the sensors required for the condition monitoring of the equipment. The data sequence diagram depicts the information flow starting from the sensors through the edge nodes and finally to the digital twin of the physical system. Now we can see that in order to successfully connect the physical counterpart of the system, which is an industrial refrigerating group, with the digital twin, a UML-based modeling approach has been adopted, as we can see here in this slide. We have used the OPC UA protocol, wireless sensor networks, and sensors for data acquisition and transmission. Now, the main entities of the UML model of the refrigerating system are presented as I told, and you can see that the refrigerating entities consist of 2 different classes, the compressor class and the cooling chamber class here. Now, in this slide, we have summarized the various industrial components and subcomponents are modeled using high-level element analysis, and the mapping between the relationship of the OPC UA and the UML are summarized in this table. Let's move on to some other details of the system implementation. We have used a cluster of Raspberry Pi 3 single board computers running on Linux operating system. Some details for the data acquisition device, STM discovery boards in order to implement OPC UA protocol, and the sampling rates were from 1 second for the accelerometer sensor to 10 milliseconds for the pressure sensor. The Iot Nodes were responsible for data handling, storage processing, and based on 5G technology, they were connected to the central cloud computer to run calculations, simulations, and feed digital twins with input, and finally to calculate the remaining useful life. Now, here we can see the developed digital twin in Matlab Simulink. As it regards the hardware point of view, for the cloud server, laptop PC was used with i7 processor, 16 gigabytes of RAM, and NVIDIA GPU. Some other details as the Zigbee low power data rate and wireless sensors is presented here in the slide. And here we can see the case study and development. In order to test and validate the proposed framework, a real-life case study has been used. The case study involves a cluster of industrial cold chain systems. The data acquisition device, along with the Raspberry Pi microcomputers, were installed on the physical machines. The configuration was used for monitoring the status of the machines and then, by extension, to log the data derived from the sensors to the cloud database and for the predictive maintenance framework. Here we can see a graphical user interface for the remaining useful life estimation based on the input and some photos of the prototype data acquisition device that was installed on one of the industrial refrigerating units. Now, let's move on to the conclusions. To summarize, an edge computing framework based on the utilization of microcomputers has been presented. The contribution is focused on the offloading of cloud computing layer and aiming to enable the minimization of the simulation time and, by extension, to the response time of digital twin. Some benefits of this approach were that the gateways, which were the Raspberry Pi microcomputers, were formed the Iot Nodes. And this system offers adaptability to a variety of different scenarios, since the OPC UA architecture was used in conjunction with the UML modeling. And as it regards the future work, we will focus on the integration of fail-safe data transmission systems, integration of an edge security framework, and implementation of the reference architectural model RAMI 4.0, which is will that be used to facilitate data exchange between different stakeholders. I would like to say that this work has been supported by the national project named SPARE, Sensor-Based Project Monitoring System to support augmented reality remote maintenance. And here you can find some key references of our research work. For more information, you can send an email to our supervisor, which is Professor Dimitris Mourgis, and we will be at your disposal to address your comments. Thank you.
Thank you, Nikos, for the presentation. Is there anyone who wants to ask some questions to Nikos? Okay. I have a small question. Can you go back to the slide of the case study? Okay. So I've seen also in your paper you gave much more space to, of course, to the architecture description and the system implementation. Okay. But I didn't understand quite well how the test case went. So you did some, you tried this system in a real case study, and I think the picture we see represents some of the results. I don't know. Can you clarify this?
Yes, this research work is only a part of this project, and of course we installed some of this data acquisition device in the industrial refrigerator units to monitor some data, and we transfer this data to the cloud database to feed the digital twin that was developed and presented in previous slides in data in Matlab Simulink. We are still in the development process, of course, but at the left side we can see a graphical user interface that has been developed based on augmented reality technology. We can
okay, there is the remaining
head-mounted displays or devices or Android devices, tablets, and so on to visualize the results that are the outcome of the digital twin or of the rule estimation.
Okay, so just a curiosity, since you say it's for implementing a predictive maintenance policy, okay, so you can use the data collected from the refrigerator in this case to determine an optimal policy of maintenance, I guess. Because now here I see the useful life, the remaining useful life, which is of course a critical information. But I was wondering, can you also get some information about the maintenance of the machine, of the refrigerator, of whatever equipment you are monitoring?
Yes, I agree. As I said before, we have also with data we gather the data from the physical counterpart, and we have also developed the wall refrigerating cycle in Matlab, simulate the wall process of all the components that create the wall cold chain counterpart.
Okay. So thank you, Nikos.
Thank you very much
for your presentation. And we can go to the next presentation, which is given by Sri Sudha Vijay Keshav Kolla. I am really sorry for how I pronounced your name because I'm quite sure that was not right. But okay, I did my best. So
yeah, better call me Sri. That's better.
Okay, yeah. Sri, right?
Yeah, that's fine.
Sri. Okay, sorry for really. No. I'm sorry. So the work you're presenting is about retrofitting of legacy machines in the context of industrial Internet of Things. Yes. Okay. So please go on with your presentation.
I hope you can see my slides and you can hear me clearly.
Yes.
Okay, good. Good afternoon, everybody. I am Sri. I'm a doctoral researcher at the University of Luxembourg. Today, I am going to present how to retrofit legacy machines in the context of industrial Internet of Things. So this is the agenda for my presentation today. I have 6 topics to talk, from introduction to summary. Let's start with the introduction. We have done a survey in the first year of my PhD with the consortium of, you can see the pilot project, where the SMEs are interested to adapt to industrial Internet of Things, but they have no idea where to start and how to start. So we have formulated 3 questions about that. Are the SMEs actually data ready to enter the prism of industrial Internet of Things? And how to empower them towards Industry 4.0? And what are the basic steps towards a connected enterprise? So these are the questions that are still unanswered in the literature. But in our background survey, we found that SMEs are neither data ready nor ready to adopt industrial Internet of Things in their existing operations. So how many companies we did the survey is around 100 companies. So that is enough data to conclude those things. So based on this information, we wanted to make them data ready. So for that, we have 2 options. One is to buy advanced machines for SMEs, and the other is to upgrade the existing machinery. That's where the concept of, we chose the later, that's where the concept of retrofitting come into picture. Retrofitting is an action to upgrade your existing machinery or to update or refurbish it. So how to upgrade is by retrofitting external sensors or adding any softwares if necessary, or and this has to be very inexpensive because it is an SME, and also it has to be easy to use. What are the advantages by retrofitting your legacy machines is that this is the starting point for your transition towards smart manufacturing from a traditional manufacturing. And this is the least financial effort as well, with the less time expenditure, and also the risks involved in retrofitting are very low. Last but not the least, but there are some challenges involved in this process, which sensors to use. And also there are several communication protocols exist, but SMEs have no idea about how and which one to adopt. And also to protect SMEs from the external attacks and threats. This is also a challenge. So these are the things that we are going to address in today's presentation. However, before that, I would like to mention few state-of-the-art literature that we found interesting and relevant to this study. The first one are proposed by Zambeti et al. And she proposes there are 2 reasons why industrial Internet of Things there are 2 drivers for industrial Internet of Things in the enterprises. First one is the push from the buzzword called Industry 4.0 itself. And the second one, there is a need, so that they're pulled by the need. So I present 3 more literature here. So first one is about need-based pull. So predictive maintenance using retrofitting a robotic cell. So here the researchers retrofitted a robotic arm so that they can maintain the robot when it's before it's too late and before its breakdown. And the second work is a holistic approach. It's mostly inspired or driven by Industry 4.0 push. So the company here did the total transformation of the enterprise, especially in the aspects of maintenance and operational safety. And the third literature is a review study where the researchers presented industrial Internet of Things and the technologies that are essential to adopt industrial Internet of Things in a company. However, there are gaps that we found in this state of the art. First one is clearly these are the focus on small and medium scale companies are clearly missing because they have a different starting point when compared to the larger companies. What is prevalent in this existing research is what they have done. Technically, what they have done is very prevalent. However, how they have done is not very much focused. Therefore, we thought of creating a basic architecture for industrial Internet of Things. Of course, that is in the context of retrofitting. And we also wanted to validate that basic architecture using laboratory as well as field tests. I jump into the architecture that we proposed in the paper. We have created this architecture in 3 layers: the physical layer, IoT layer, and the cyber layer. Let's dive deep into physical layer. What contains the physical layer? At the beginning of the retrofitting, you do not have any infrastructure other than the machines. So the machines are legacy machines and they have neither data connectivity nor have the capacity to generate to transmit the data. Therefore, the first thing is to retrofit sensors to the existing machines. So they also fall under a physical layer. The next step is an optional step is an IoT device, adopting IoT device. They are non-standard devices that can connect to your network and have the capacity to transmit the data. However, a good example of an IoT device is your mobile phone itself. However, it is an optional step, and it is very useful if a company wants to digital transform the whole enterprise. So it comes handy. And then with a field bus, we connect to something called IoT nodes. These are the critical points in the architecture because the IoT nodes are where the data gathering happens. And from those IoT nodes, we can have PLCs, microcontrollers, edge devices, or a normal computer for the IoT nodes. And from there, we connect it to a communication protocol. The communication protocol could be OPC UA, which is widely accepted, or simple Ethernet connectivity. So from there, we jump to the IoT layer. In the IoT layer, we have two important things. One is IIoT gateway, where we include the security aspects of the data, data gathering, processing, and delivering. And then you have IIoT middleware. This is very important. This is where we connect your physical entities to the cyber entities. So physical entities, so for example, sensor data can be fed to IoT middleware with a simple JavaScript. We can convert that to understandable units and then push them to the databases. Finally, we have a cyber layer, which includes a database. And this database could be local as well as a cyber. So some companies prefer to have the database locally to avoid threats from external hackers. So we have, in our field test, I will show you, we adopted a local database. However, you can also have a cyber database. And this database, from here, you can send the information to analytics, monitoring, etc. So here you just add on the applications. This is the general architecture in the context of retrofitting. Now I will show you the laboratory implementation. We have to implement it in the laboratory. We have taken a drilling machine that has no sensors attached with a maximum RPM of 3,200. And then another hardware we chose was Raspberry Pi. And we also added a few things to the Raspberry Pi. One is touchscreen to be able to interact with the Raspberry Pi, and then an analog to digital converter in the form of a Pi hat. I will let you know more about why we added analog to digital converter. Before going deep into the architecture for laboratory implementation, what to measure from the drilling machine. So we have chosen to measure speed of the drill as well as the drill depth as the critical variables. To measure speed, we adopted a Hall sensor. You can see a Hall sensor. It has a 5 volt input, but however, to connect it to Raspberry Pi, we needed to convert that 5 volts to 3.3. Here we adopted a voltage divider and converted it into 3.3 voltage digital. So it's a digital output, so we can directly connect it to our Raspberry Pi. However, when it comes to infrared sensors, this is to measure the distance or the depth in our case. It can measure from 10 centimeters to 80 centimeters with the highest accuracy. However, this is an analog sensor. This is not a digital sensor. That is why we had to adopt an analog to digital converter. So these are very details. For SME, it might be a bit difficult to get into these details. That's why the upscaling of SME employees is very important. So analog sensor, and then we converted to digital output using A to D Pi hat. The another software we used here, coming to the softwares, we used Node-RED, InfluxDB, and Grafana. These are the 3 softwares we used, all open source. There are no cost involved in this. So Node-RED, as I said, this connects your physical layers to the cyber layer. So it reads the sensor information, transforms, and saves or pushes it to database. And the database we used to collect the data is InfluxDB. It's an open source database as well. And then from the database, we send that information to Grafana. It's a visualization tool, very versatile and flexible tool. You can program the way you want and what the data you want to see, and you can also create alarms when a critical variable is going above the threshold. So this is how the interface of Node-RED looks like. You take the information from Raspberry Pi. So for example, here we are taking information from pin 7. Of course, we are getting frequency, which means that we are measuring speed here. So the function here helps you to program in a JavaScript to convert the frequency to speed, and we push that information to InfluxDB. The same with the distance as well. The function here we coded in order to measure, in order to get an output that is understandable, like speed in RPM and depth in centimeters. Experimental setup in the laboratory has few changes because we figured out that we could install Node-RED in Raspberry Pi itself. We don't need to, for example, if you see before, we mentioned it in the Iot layer, but this architecture is quite flexible. So when it was permitted to us, we install Raspberry Pi and we install Node-RED in the Raspberry Pi itself in order to reduce the complexity. Other than that, it looks quite similar to the architecture I proposed. And the results and field tests, what we have achieved by using this architecture and doing the laboratory test, we were able to gather real-time information about the machine, especially in terms of speed and drill depth. Of course, we also pushed data successfully to the databases. This was very cost effective because we used open source softwares and sensors weren't too expensive. And then we validated the basic architecture in the laboratory. However, this has come with some challenges. The concept was relatively new, so that there was no standard way of doing things. So we had to create a way that we felt was standard. And the next problem came when we could not find the combination of hardware that can function together. This is a challenge. Even in large companies, sometimes not all hardware speak to each other. Therefore, you need to improvise here. So the improvisation using, for example, where we use JavaScript so that we have an output that is understandable to us. And selection of critical variables. For example, in drilling machine, it's easy. You select speed and drill depth. But however, if you have a production machinery, you have many variables, and selecting few among them can be a challenging task. In the field test, this we did not write in the paper because the field test happened in between July and September. That's why, however, it's finished now, so we can present. As I said, in the field test, we adopted a local database for a quick information gathering. However, we connected that local database to MySQL because the company was using MySQL software. And also you could see we also adopted a Siemens Symantec IoT 2000 as an IoT device so that it includes security aspects of it. In the communication protocol, the company was using S7 communication, which is from Siemens. So we adopted the same. And to summarize, we created a general architecture for IoT in the context of retrofitting. This applies to the legacy machines and a critical focus on SMEs. And the architecture is adaptable for different machines with slight modifications. I have shown you two modifications of the architecture in my presentation, one for laboratory and one for the production scenario. And this has been validated in the laboratory as well as the company. And we also disseminated the knowledge on how to IIoT ready in this, which is very interesting to SMEs. And we have presented the challenges encountered during the research and how we tackle them. With this, I would like to thank you, ISM organizers, for giving me opportunity to present this. And if you have any questions and want to collaborate, you could contact us here. And we thank ProtPilot, the project, and the support given by Interreg 5 program in this to deliver this research. Thank you. Thank you, everybody.
Thank you, Sri, for this really interesting presentation. Is there anyone that wants to ask some questions?
Yes, I have a question for the.
Okay.
First of all, thank you for your presentation. Very nice, very interesting. I have a curiosity. Recently, we have planned to use Grafana for the dashboard, to create a dashboard in a digital twin architecture. I just would like to know in which way did you connect the Grafana with the rest of the architecture? Because I suppose you have to connect the Grafana with the source of the data. I mean.
Yeah, exactly. So we actually used Grafana and we installed it in the Raspberry Pi itself. So
okay.
Raspberry Pi supports installation of Grafana, so we installed it in itself, and we communicated to Grafana using command prompt. So we pinged Grafana from the command prompt.
Okay, and is it easy to be used? There is a forum if I need something. Is it open source? I mean.
Yeah, the documentation was not quite available. We did trial and error, and in our case, after doing a lot of trial and error, we were successful connecting to Grafana, and then it wasn't easy. It took us a while to figure out how to connect. But however, if you could write me, I will clearly explain you how we connected Grafana to the system, to the whole architecture. Yes, it was difficult, but it wasn't impossible.
Okay, thanks.
Any other questions? Okay, I also have a really small curiosity. First of all, it's a really well done job and interesting work you did. Also because I think there are, as you said, there are a lot of small and medium enterprises or maybe companies with not many financial resources that would be interested in entering the IoT world. And this could help actually. So I was wondering if you already did cost analysis on how. I mean, I know that this would be for sure less expensive than investing in new machines. But are you planning, or did you do, I don't know, a small cost analysis to understand what is the average or the indicative cost of adopting this solution for a company?
So very interesting question, and also very difficult to answer because
I know
because SMEs, as I said, there are two ways of retrofitting. One is a need-based pull, the other is Industry 4.0 push. It would get expensive if you want to digitalize the whole SME and every mission is connected to the database. It would get really expensive, and in that case, retrofitting is a cheaper solution when compared to advanced machinery. We have not done cost analysis of a whole enterprise, but for example, if you take the field test that we have done, for that we have done a cost analysis. The field test in a local company, we have retrofitted 6 sensors, and most of the sensors we printed them. We 3D printed them actually because we had to utilize the resources that are available. However, you cannot 3D print an electronic device for now, so we had to improvise there. For example, for tension, we have 3D printed something like a horseshoe, which will compress, and then we measure the distance using an electronic sensor. So it is all about how much you can think out of the box and can reduce your costs. So for the company to retrofit the whole production machinery, I mean the one machinery, we use 1,200 euros. If you would have to adopt a new machine that comes with all the critical parameters, it would have costed them around 25,000 euros.
Okay, that's a win.
A lot of savings for the company. Yeah.
Thank you. Thank you, Sri. Well done. And I think we can move to the next and last presentation by Claudio Savaglio, which I see is connected.
Yes, I am. Hi.
Presenting a work about cloud and edge-based ERP systems for Industrial Internet of Things and Smart Factory. So please, Claudio, can you share your screen? Okay.
Can you see it?
Yes.
Okay, it should be. Okay.
Okay.
Good morning, everybody. My name is Claudio Savaglio. I am a researcher at the National Research Council of Italy, and the paper I'm going to present you is entitled Cloud and Edge-Based ERP Systems for Industrial Internet of Things and Smart Factory. My co-authors are Dr. Prakasha, Dr. Garg, Dr. Bawa, and Dr. Spezzano. This is an outline of the outlet of the presentation, a very brief introduction on enterprise resource planning systems, which is the research domain of our paper, a rapid background on cloud and edge computing paradigms, and hence a review about the application of ERP systems within industrial Internet of Things and smart factory, and in particular emphasizing the current state of cloud and edge-based solution for ERP. Finally, a discussion and, as usual, conclusions and future research directions. So what an ERP, enterprise resource planning system, is? ERP are a well-organized collection of softwares whose goal is timely integrating business processing with the final goal of supporting the management of effective cross-functional operations within an organization. In other words, ERP are software packages that enable company to integrating their data through the entire organization, and in such a way, ERP allow providing the correct input to the management layer, so supporting management action, coordinating the company resources, and also promote standardized best practice and action aimed at the cost reducing. Is widely recognized that probably ERP systems is the most important innovation in the corporate use of informatic technology in the 90s, and it's the reason why companies that deal with ERP make a lot of money, and they are very big company like Oracle, SAP, and so on and so forth. But how a conventional ERP system actually work? Basically, you can imagine an ERP system as a very big single database that works as a central location for the storage, distribution, and forwarding of the data between the various department and business processes. So you can imagine an ERP like a very big monolith database that works among financial district, human resources district, purchase district, and so on and so forth. Obviously, the management of such a complex sharded and monolith system is very costly and challenging. So over the years, several solutions have been developed with the aim of avoiding such a centralized approach to the data and resource storage. In particular, recently, cloud and edge computing paradigms have been used and exploited to implement ERP systems. What is cloud computing? Cloud computing, as most of you know, cloud computing is a recent, nowadays it's 20 years old, 20 years old computing paradigm that is based on network, and the idea is to provide hardware, software, and the networking service to the clients through internet. In such a way, user can benefit of always on, anywhere, and anytime, and any place services, regardless the complexity and the implementation detail or the underlying infrastructure. in such a way user pay for what they use. They can elastically scale up their infrastructure, and in such a way they can, let's say, improve the agility of their business and shorten the time to market. Edge computing goes in the opposite directions of cloud computing, because edge computing is an emerging paradigm that is based on the concept of proximity, while computing was based on the network and hence on remote resources. Edge computing is a proximity-based computing paradigm, according to which data should be locally treated as much closer as possible to the point, to the location in which they are generated. In particular, these data are treated by the edge servers, also known as edge platform, and due to the proximity, edge server can perform context-aware and lightweight tasks on the raw data. And if needed, they can offload to the cloud or to the enterprise data center a reduced amount of data, or the main findings, the refined model, and so on and so forth. Thanks to its features, the edge computing allow obviously reducing the data communication, the privacy and the security risk, and as a result, the bandwidth and the energy consumption. So it has very nice features, especially for the novel application area. Just from this quick overview on ERP systems, cloud and edge computing, two main considerations emerge. The first one is that ERP systems are very useful in any organization, in any domain, but specifically and especially in the complex and cyber-physical domains such as industrial IoT and smart factory, because ERP can deeply and positively affect the core business by supporting processes related to the monitoring of the production chain, the identification of critical issues within the workshop, and as a result, they can contribute, ERP can contribute to downtime prevention and the workload balancing in smart factory. As a second consideration, main benefits of cloud and edge computing perfectly match with the needs of ERP systems and with the goals of smart factory. Indeed, if we couple cloud and edge computing with ERP system, we can enable the processing and the storage of large amount of data. We can enable the continuous and real-time information sharing between customer and consumers. And as a result, we can respond to the consumer behavior and the organization needs in a rapid and agile way. Hence, it can be stated that the exploitation of cloud and edge computing within an ERP would support the creation of an even more smart factory, which could be more context sensitive and more reactive. So the exploitation of the decentralized communication can be of great importance for the smart factory. On the basis of these considerations, the two paradigms of cloud-based ERP and edge-based ERP recently gain attention. What is cloud-based ERP? Basically, cloud-based ERP offers the same solution and the same functionality of ERP, but by leveraging on cloud. So ERP system can be provided according to infrastructure as a service, platform as a service, on service as a service model, cloud model. Okay, and obviously the benefits for the companies are great, because they don't have to invest a lot of money in IT infrastructure or in maintenance cost. According to Fauchette, and it is also to other, according to other, let's say, researcher, cloud-based ERP can provide new business value and can provide a competitive advantage to the company. In particular, Al-Mashari found that the mainly adopted cloud-based ERP models are the infrastructure as a service and the software as a service model. And the driving factor lie in the size of the business and in the requirements, in the privacy and security requirements that any organization has. Regardless of the specific model, infrastructure, platform, or software, the main pillars that are well established for cloud-based edge compute, for cloud-based ERP, are virtualization, agility, on-demand, and pay-as-you-go. But anyway, CRP is still in its infancy, and nowadays there is no agreement on an exact definition for CRP. Edge-based ERP is an even more recent field of research, and the idea here is to couple edge computing benefits with the distributed infrastructure, and so as to provide ERP in a more cheap way by offloading part of the effort from the core of the cloud ERP and forwarding the most computational intensive task on the cloud. Obviously, there are benefits on security and privacy preserving, and edge-based ERP enable faster decision making. In particular, an interesting finding is that ERP is better suited to small-sized business with the sensitive data to protect. And as another finding is that even more than cloud-based ERP, edge-based ERP has the potential to provide small-sized organization with a substantial competitive advantage. So edge-based is even more suitable for small-sized companies. In particular, an interesting research area is the exploitation of ERP module on the exploitation of some of ERP module on the edge and some other on the cloud, and this is the so-called hybrid cloud edge ERP. So, summarizing, by analyzing the limited literature currently available, it emerged that the advantages of C and E ERP for IoT and smart factory are the cost savings, the enabling of new business model, the improved agility and flexibility, and the higher productivity and efficiency that they can provide. On the contrary, there are some disadvantages. For example, organization issues and conservative mindset are a very big obstacle, because obviously it's very hard to re-engineer processes or to ensure the business continuity if the paradigm of the factory is changed, as well as few companies want to storage their data in external locations. There are some infrastructural needs. For example, traditional on-premise ERP system consists of specialized hardware and proprietary software that work over local area network. So this change is also has a big impact. And finally, most of companies have concerns about the vendor lock-in and interoperability because they don't want to be dependent on a single cloud provider, or they don't want to have only partial access to their resources. This table gathers the previous considerations and highlights that the same benefit is provided in varying degree according to the cloud and edge-based implementation. To conclude, we have seen that ERP system focuses on the integration of system and services, automation of business process, and secure sharing of data to the entire organization. Due to these features, the ERP competitive advantage is further increased by coupled with new technologies like the industrial Internet of Things, because in this way we can match the constant need for change in the organization operation. And we have introduced the cloud and edge-based ERP. As for every technologies, also the adoption of C and E ERP implies both pros and cons that should be carefully analyzed. From a technical perspective, these two paradigms are both very promising enabling technologies, but obviously there are some obstacles like the conservative mindset and the availability of internal technical knowledge or resources. So this is a very big obstacle to the adoption of C and ERP adoption. But anyway, organizational characteristics and industry sides are two key factors for the adoption of cloud and edge-based ERP. As future work, it will be very interesting to study the novel hybrid cloud edge reference architecture to support ERP system, so that to overcome the limitation in the current C and ERP system and fully exploit the other Internet of Things potentials. Thank you for your attention.
Thank you, Claudio, for the presentation. So anyone wants to ask some question to Claudio? Okay, then I'll go. Just a curiosity on my side. I can see the advantages that you described about cloud and edge ERP. I was wondering if you have had the chance to discuss these advantages and benefits with some companies, for example, I don't know, through workshops or surveys or anything, in order to understand their willingness to adopt a new technologies like this, since you named a few barriers for the implementation.
Yes, thank you for the question. You touched the hottest point. This is a joint work, and basically we are in the first stage of this work. So we started from the literature review, and we found the contents I've provided in this presentation. Our next stage will be the discussion of these systems with small, medium, and large enterprise. In particular, we have individuated some small, medium, and large scale enterprises to discuss with, and we have selected companies working on smart manufacturing and computer science, like entity data. And we are currently setting some interview with all the, let's say, all the figures of these companies. They seem interested, but we planned to do this because it's our current work.
Yeah, of course.
At the state, we just based it on a review analysis, but
yes, that's right.
We aim to do this. So,
yeah, I think it would be interesting to see feedbacks from companies as well.
yeah, because the data in the literature only refer to two markets, that is the USA market and the Indian market. So in these two markets, we found the let's say the conclusion we reported in the paper,
Okay.
but we are more interested in local market like European. So we are investigating on this.
Okay, thank you. So with this presentation, we have done with our session. Thank you again for participating, everyone. And I don't know, Vittorio, if you want to add something?
No. Everything was perfect, was fine. Then.
And we're right on time. It's 1 p.m.
Yes.
Okay, so thank you again and have a good day.
Thanks, everybody. It was a pleasure.
Bye-bye.
Bye.
See you.
Bye.